Hi, I want to give an overview of something that we call substitution reactions. Now, we're going to have to take a few lectures to really come to grips with what these reactions are and how they work. But to start off, I think we need to just look at a general scheme for what a substitution reaction is, and then we're going to start to unpack it. Now, at the outset, I want us to just be very clear here that substitution reactions have a number of different layers of complexity to them. So there's actually quite a lot of information that we're going to have to unpack out of something as simple as this. But essentially, in a substitution reaction, we have a couple of components. The first thing that's important in a substitution reaction is that what this R group over there is. And that R group is always going to be a saturated carbon. And by that, any carbon that is saturated, what we mean is that it is sp3 hybridized. In other words, there is no pi bond on that carbon. So up until now, we've been looking at reactions where we have some kind of leaving group on a molecule, but we've been looking at an unsaturated carbon, actually just the carbonyl, C double bond O. But now this is just going to be a carbon. And connected to the carbon is what we would call a leaving group. And so we're also going to have to kind of unpack exactly what a leaving group is and expand on our knowledge of that. But for now, we can think of leaving groups as being very simply those classical examples that you've seen of chlorine, bromine, and iodine. And then the next important thing in a substitution reaction is that we need to have a nucleophile. And in this course, you've started to become a lot better at identifying what a nucleophile could potentially be. And again, this could be a very wide range of different nucleophiles. Typically, the nucleophile would have some lone pair that is available to donate to the electrophile, which is the saturated carbon, which has its leaving group on it. So what typically happens is this lone pair, and that lone pair could be a negative charge, it could just be a neutral lone pair, would add its electrons to this carbon, and the leaving group would leave, and we would get something like that. Now, of course, the leaving group, when it leaves, needs to leave with its electrons, and those electrons would be represented by a lone pair. That lone pair, very typically at this point, would be effectively a negative charge. But what we have over here is a substitution. So we've got a carbon with a leaving group on it, some nucleophile has come in, and a substitution has occurred over here. Now, in this course, we're going to need to just sort of unpack a little bit more about this. But because this is rather random, let me just show you at least one real-world example of that. So this example that I've drawn over here is you've got a benzyl bromide over here. There's the benzyl group. The bromine we know is a good leaving group. We can recognize hydroxide, really very simple. It's typically a base, but we can see it as a nucleophile with a negative charge. It's able to add to the carbon and then kick out the leaving group. And we'll have to unpack certain examples like this later on. There's a lot more detail that is missing over here, but we will get to that. For now, I want to start with just us looking at the way, this mechanism that's occurring in this reaction and what types of mechanisms can occur. Because it turns out that there are two main types of mechanisms that occur. Now, to discuss these types of mechanisms, I'm going to use a rather silly analogy, and I'm going to think about a substitution reaction in terms of relationships. All right, so let's imagine that we have a relationship over here between two people. So we've got, say, the girl over here who has a relationship with some loser guy over here. So it's not a great relationship, and because of that, the bond between them isn't very strong. Now, there are two kind of ways how this relationship is going to end. The one way that this relationship is going to end is where the girl recognizes that this is a really bad relationship and she does not want to be with this loser guy anymore. So what happens is she breaks off the relationship. So what happens is this arrow that I've drawn over here is the first arrow that happens. And so the loser guy goes away and the girl remains behind. And then at some point she finds the new guy, and who's way better, and he forms a bond with her, and we get a new relationship being formed over there, and it's a better one. There's another way that this relationship could end, and that is that the girl is kind of hangs on with the loser guy because she doesn't want to get rid of him for whatever reason. But what happens is the new guy, the better guy, comes along, and she likes him a lot more. And so there's this transition period where what happens is the new guy kind of comes in and the old guy is told to push off. The loser guy is told to push off around about the same time. And so those are the two types of mechanisms. This is a crude analogy, but those are the two types of mechanisms that occur in substitutions. All right, so option number one is where the leaving group over here goes away and we are left with the electrophile plus the leaving group. Now, if we do that, the leaving group will almost certainly have a negative charge on it, which means that the R group over there will have a positive charge. And what happens next is our nucleophile can now come in, donate its electrons like that, and that gives us our new relationship. And the other option, option number two, is where all this happens in one. So we've done that up there. Let me just do it again. Okay, so there are these two different mechanisms that can take place in a substitution reaction. And the question that you might be asking is, well, who cares? Why do we really want to know about these two different mechanisms? Well, the problem is that I've shown you an example over here where I've shown the substitution happening. I've just told you that this happens. What we need to get to a point of where we can look at a potential electrophile with a leaving group on it and a nucleophile, and we need to make a decision about whether that reaction is possible or not. And in order to do that, we need to be able to analyze these two types of mechanisms and kind of figure out what is going on in the scene. Now, this we're going to deal with. I have this acronym which is going to be helpful to try and work out these two different types of mechanisms and what kind of scene is going on. Are we having a substitution where the new guy is coming in and the loser guy is leaving at the same time? Or are we first breaking a bond and then a nucleophile coming in? I'm mixing my analogies. I apologize for that. And so this acronym is what we're going to look at. And it's going to take us a while to unpack this acronym in its full sense. But I'll give it to you now what the different things were. So the S is for sterics. The C is something that we're going to have to really kind of pick out a bit, but it stands for carbocation. The E is connected to all of these three together. This is the electrophile. All right, I'm going to put a question mark. Is sterics and carbocation and electrophile actually all interrelated? And we'll get to that. The N is easy, that's the nucleophile. And the E is actually extremely important in all of this, and we're going to have to unpack that as well, but it's what I call the environment. So we're going to discuss and unpack this acronym at a later stage. But for now, we need to be able to recognize the difference between these two mechanisms. Once we understand the basic things that kind of affect them, we can then start to work with this. So let's just understand, how do we know about these different mechanisms? And the answer comes from kinetics. Now, before you have a panic attack over here, this is actually extremely easy. Don't worry about it. Let me just show you how simple this is. So let's look at that very first mechanism that we looked at. And in this mechanism, what happened was that we first had the leaving group leave, and then the nucleophile came in and did the substitution reaction. When we look at this, what I want us to do is to consider what happens when we do kinetic measurements. Now, kinetic measurements are, we want to see how fast the reaction occurs by changing variables in the reaction. And in this case, what we're going to change is the concentration. So we can do a reaction where we hold the concentration of this constant. So for instance, 0.1 molar, arbitrary. But whatever it is, it's constant. And then we do a lot of different reactions, but we change the concentration of the nucleophile. We make it more and less concentrated, and then we plot how the reaction rate changes with that. So to do this, we've got to basically do two series of reactions, a lot of different reactions, but the one series is where we keep the electrophile, completely constant, and we make this more or less concentrated. And then we switch that around. We keep the nucleophile completely the same, and we increase and decrease the concentration of the electrophile. So this is the results that we get when we do this. Okay, so let's just look at these two graphs and let's make sure that we just understand them. So on the y-axis over here, we've got a rate. So as we go higher up, the reaction rate is increasing. And on the x-axis, as we go across, the concentration of the electrophile is increasing. Over here, we've got the exact same example for the nucleophile. All right, so if we look at that, this is interesting in terms of this reaction, because what's happening is that the concentration of our electrophile, as we increase that, the reaction seems to go faster and faster. However, when we increase the concentration of the nucleophile, nothing happens. The reaction rate does not increase at all. Now, what this is telling us is that this reaction over here, all right, the way this reaction is occurring has nothing to do with the nucleophile. It doesn't matter how strong or weak the nucleophile is. The reaction rate is not important over there. What's important over here is this process over here. We need to first have the leaving group leave. Once the leaving group is left, then the nucleophile can come in. In other words, going back to our analogy of relationships, for this to happen, the girl is not wanting to, needs to first break off the relationship with the loser guy before she'll allow someone new to take his place. So, because that doesn't matter, it doesn't matter how many good new guys there are out there, if she's still with the loser guy, nothing is going to happen and the reaction is not going to occur. All right. Now, because this mechanism over here relies solely on one of the components, not both of them, just the one component over here. That is, first of all, we must have a breaking of the first bond, and it doesn't involve both components. This one is called substitution nucleophilic unimolecular, meaning one, and its abbreviation is a capital S, a capital N, but at a subscript, and then a 1 like that. And we would typically talk about this just being an SN1 reaction. Now, it is confusing in the fact that an SN1 reaction takes place in 2 steps, all right? But remember that the reason that it's a 1 over here is because this reaction does not depend on both the electrophile and the nucleophile, rather just the electrophile. We've first got to break that bond. Let's look at the second type of reaction mechanism, and this is one where the nucleophile comes in and the leaving group leave at the same time. So this is sort of a one-step reaction over here. What are the kinetics of this type of reaction over here? Well, this is what they look like. These are just random examples and not like very specific ones. But the point here is that when this type of mechanism is occurring, when we look at the kinetics of the reaction, we see that if you increase the concentration of the leaving group, the rate of the reaction increases. If you increase the concentration of the nucleophile, remember, if we keep doing this one over here, we're keeping this one constant, all right? These are 2 separate series of reactions. If there's 10 points over there, 10 points over there, we've had to do 20 different reactions to measure how fast they are occurring. And so if we increase the concentration of the nucleophile, it also increases as the reaction, as the concentration of the nucleophile increases. And what that means is it speaks to this type of mechanism over here. The more nucleophile you have, the greater the concentration, the faster this reaction will happen because these will bump in faster, all right? We're going to have more bumps in with that. So that's why this will happen. And also, as you have more of those, there will effectively also be more of those around. So it will bump into the nucleophile more effectively. And so in this reaction, we would call this Substitution nucleophilic bimolecular. And its abbreviation would be a capital S, small n, and A2, SN2, which I'm sure you've heard of already. So substitution nucleophilic bimolecular is because both components, the electrophile and the nucleophile, are involved in the rate of the reaction. And so this is a one-step reaction. All right, so we've looked at the very basics of substitution reactions. We've seen the SN1 mechanism, we've seen and the SN2, and then we have also had a look at just the overall layout. In the following lectures, we're going to start to pick out how we decide between these two different mechanisms over here by using this acronym and understanding the things that define whether these mechanisms will occur. And that is going to help us to understand whether substitution reaction can or can't occur. And that is the most difficult part about the substitution reactions. Looking at it is fine, but unfortunately, we do need to have a deep understanding of all these different components in order to effectively figure out what happens in a substitution reaction.